What's up, my pre-calc people? My guess is that you're probably really close to having a Unit 1 test for AP Precalculus over polynomial and rational functions. And that's going to be your first big test of the year, and you're probably going to want to do really well on it. Now, the one type of question that a lot of kids struggle with are free response questions. So in this video, I want to go over 2 free response questions that are probably going to be really similar to the ones that you're going to see on your Unit 1 test. Now, if you want actual PDF files of these 2 problems I'm going to go over, head on over to the Ultimate Review Packet for Precalculus using the link in the description below, and you can gain access to this document. There's lots of free preview items in the Ultimate Review Packet, and this is one of them. That way, if you want, you can try them on your own, hit pause on the video, come back when you're done, and then go ahead and see how you did. All right, let's take a look at these 2 free response questions right now. That way, when you tackle your Unit 1 test in class, you're going to crush it. So in this first problem here, we were given a function f of x defined as x to the 4th plus 4x cubed minus 21x squared, and we're asked several questions about it. The first is to determine the end behavior of f as x increases without bound. Express your answer using the notation of a limit. So the first thing we got to be familiar with is writing that limit, right? So we're going to write the LIM. Now they do want me to find the limit as x increases without bounds. That's as x goes towards infinity. That's the right end behavior for this particular function. All right, so now we know this is a polynomial function, and we know that it has an even degree. Now what we know about an even degree is that both ends do the same thing. So both ends are either up or both ends are down. And how do we know? Well, we got to look at the leading coefficient in front of that term, and we see that it's a positive 1. Now because it's positive with an even, we know that both ends are going up. That means the right end behavior is actually the same as the left end behavior, and that is going towards positive infinity. If there would have been, let's say, a negative 2 out in front of that x to the 4th, then that means both ends would be going down, and the end behavior would be negative infinity. All right, the next question says to find the zeros of the function and determine the multiplicity of each. Show all of our work. Now, I'm sorry to break this to you, but you're going to have to be able to factor if you're going to get the zeros. So the first thing I notice between all of the 3 terms is that they all have at least an x squared. So I'm going to factor out that x squared. I'm left behind with an x squared plus 4x minus 21. Then I'm going to continue to factor, and I know everybody's got different factoring strategies, but I like just go old-fashioned trial and error. So the only way to break apart an x squared is an x and x. The very first thing that pops in mind for 21 is 7/3, and obviously just kind of thinking about a 7/3, you could clearly get a 4. I do want the 7 to be positive and the 3 to be negative. That way they multiply to get that negative 21, but when you add that inside 7x and that outside negative 3x, you get that positive 4x in the middle. Now, this means that there are 3 zeros. First, we have x minus 3 could equal 0, and that means x equals 3. Then we have x plus 7 could equal 0. That means x equals negative 7. And then finally, we have x squared equals 0, which means x equals 0. Now, the x equals negative 7, the x equals 3, those both have a multiplicity of 1 because they have an odd power. There's really a 1 right here, you just kind of can't see it, but there's only one of those factors, right? There's only one x plus 7 factor, there's only one x minus 7 factor, or x minus 3 factor. But the x squared, there are 2 of them, right? I can actually break apart that x squared and write that as x times x. So that does have a multiplicity of 2. So our 3 zeros are 0, negative 7, and 3, and we're identifying the multiplicities as 2 for the 0, 1 for this negative 3, the negative 7, and the positive 3. All right, the next question says to determine all such intervals such that f of x is less than or equal to 0. So basically we're taking our function x to the 4th plus 4x cubed minus 21x squared, and we're figuring out where it's less than or equal to 0. Now remember, what does less than or equal to 0 mean? That means negative. We're looking for where this overall output, whatever that output is going to end up being, is negative or equal to 0. Now the good news is I already factored it, so I'm going to quickly just show those factors one more time here. No point in going through that again. You guys already know it all. And that means that we have 3 zeros. So what we're going to do here is we're going to make a number line. So many kids don't know how to solve polynomial inequalities. It's always crazy to me. But we're going to put those numbers in order. So we're going to go negative 7, 0, and then positive 3. Now the first thing I'm going to do is I'm going to put filled in dots at those values because it says that I am allowed to equal 0. So any of those 3 values would actually be considered solutions to this inequality. Now, there's a couple different things you could do. You could actually test the intervals. You could pick a number below -7 and see what it produces. Does it produce a positive or negative? But this is where I hope we actually already know a lot of things from this particular unit. Now, we know the end behavior. We already know the end behavior that we talked about, and that both ends are going in a positive direction. So that means anything greater than 3 and anything less than -7 is going to be positive, because we know both ends are going towards positive infinity. Then we could also bring in multiplicity. Remember, -7 has a multiplicity of 1. That's odd. When you have an odd multiplicity, that means that one side is positive and one side is negative. There is a change in sign when you go through any zero with a multiplicity of 1. So you actually go through that 0, you cross through. That means on the other side of -7 has to be a negative. It just has to be, because that's what happens when you have a multiplicity that is odd. Same thing with the 3. We already know the right side of 3 is positive. Because 3 has a multiplicity of 1, which is odd, the left side must also be negative. And then this even fits exactly what we know about 0, because 0, remember, had a multiplicity of 2. And when you have an even multiplicity, both sides of that 0 have the same sign. So if the left side's negative, the right side's got to be negative. So I was able to figure out the intervals without having to do any test points. So if I want to kind of think of a really, really rough picture of the graph, here's the graph over here. It crosses through, it's negative, and then it touches, it doesn't cross, it's still negative, but it does go up and touch 0. And again, it doesn't cross, doesn't change sign, and then eventually comes back here at 3 and crosses through. Again, terrible picture, but you get a rough idea what this graph is doing. Now, I'm looking to be less than 0, so I'm looking to be in this area right here, or again, equal to -7, 0, and 3. So the final answer to, the set of values that are going to make this function less than or equal to 0 is going to be anywhere -7 to 3, brackets on that -7 and 3. Now, what about 0? Well, 0 is already included, right? I am allowed to equal 0, so I don't have to mention 0 because it's already falling in between -7 and 3. So anywhere in this interval right here is where we see we are less than 0, negative, or equal to 0. So it's kind of a tough problem a lot of kids struggle with, but hopefully I made that pretty simple for you. All right, the final question from this first FRQ is determine the number of relative extrema for F and justify your answer. So I'm actually going to go right back to the picture I already drew here. Now, between two zeros, there has to be some type of minimum or extrema, basically, min or max. And because I kind of already had this rough picture here, we know there's going to be an extrema here because it goes from positive up to that 0. So it's got to turn around and go and hit that 0 right there. And we know there's another one in between here. And then because we had that multiplicity that was even at 0, we know that it must hit right here as well. So we know that we have 1, 2, 3 relative extremas. And again, these ends are going up forever because we already know the end behavior. But again, it's got to make that turn in between the -7 and the 0 and the 0 and the 3. And then because we know that we have that even multiplicity of 0, it's going to go up there and touch and come right back down, creating another extrema. So we know for sure that we have 3 extremas. And it says justify your answer. Well, I just kind of did in words by showing that sign chart. But you could also talk about the fact that we know that in between the zeros, there's going to be those extremas. And then because that multiplicity of 0 is 2, that's going to also produce an extrema at that value of 0. All right, that's it for that first FRQ. Pretty good one. Hopefully all those made sense. And again, I really recommend you, getting out this worksheet and doing it on your own and then seeing how you did. All right, let's jump into number 2. So number 2 gives us a graph of h of x with several key points labeled. We see some extremas labeled, we see an inflection point there at 1, 3, and we also see the 3 zeros of -4, 2, and 5, and there are tons of questions. The first one's to know where is the function increasing, and then the second one's to know where it's decreasing. So we see the function is increasing right here, and then it's also increasing right here. Everywhere in between, we see that the function is decreasing. So all we got to do is give those x coordinates for where that's happening. So it's increasing from -infinity to -2. And then it takes a break, and then it's decreasing from -2 to 3.5. And then again, it's also increasing from 3.5 to infinity. So there's where I'm increasing those two areas I shaded in kind of teal there, or turquoise, whatever you want to call it. And then in yellow, I shaded where it's decreasing. So pretty simple there, but just keep in mind that we're using the x values for where we are making those changes. All right, next question says, where is the graph concave up and where is the graph concave down? So first, concave up is going to happen somewhere after this inflection point, and it's all concave up there. Now keep in mind, concave up means that the rate of change is increasing. And of course that makes sense here because we have the rate of change being less and less and less negative, and then it turns at this 3.5, it turns and becomes more and more and more positive. So the rate of change is constantly increasing from really negative to, well, really positive. Then we also have the graph that is concave down, and that's going to be over here. And concave down means that the rate of change is going down. So we see the rate of change starting out very, very positive and becoming more and more negative. So the rate of change is definitely going down there. All right, so concave up is going to start at 1 and go towards infinity. Again, 1 is that inflection point where we switch right there in the middle. And then where it's concave down is going to be negative infinity up until that value of 1 at that inflection point. All right, next set of questions says, what interval or over what interval is the function less than 0? All right, so less than 0, we're talking about the function values being less than 0. So where do we see the graph below the x-axis? Well, we see below the x-axis right here, and we see it below the x-axis right here. Now, it does not want me to equal 0, so I don't want to include those zeros. So from negative infinity to negative 4, and then again from 2 to 5. Over those two x intervals, negative infinity and negative 4, all over here. And then from 2 to 5, all over here, we also see that's less than 0 or negative. All right, next up it says, over what interval is the function increasing at a decreasing rate? Okay, this is a really tough question. So decreasing rate means concave down. Just a fancy way of saying it, right? Because when your rate is decreasing, you're concave down. But we want the function to be increasing. So we've got to really have a good eye for where this is happening. So we want to be concave down and increasing. That's going to happen right here. All of this right here, we are concave down and increasing. Right here, we are concave down, but we're decreasing. So we don't want to give that. And then here, we are all concave up. So we have an increasing rate, but we don't want that, right? So what we see here and shaded in yellow, or I don't know, I feel like I should shade that in different colors so that you see it better. I don't know, right here, all of this, right? All of this we are increasing and we are concave down, meaning our rate of change is becoming less and less positive. It's going down. So negative infinity to negative 2. That's the interval where we are increasing and concave down. All right, so two more questions over this particular graph. Over what interval is the graph decreasing and concave up? Okay, decreasing and concave up. Decreasing and concave up. That's going to be right here. So the graph is definitely decreasing. It's going down from left to right, but it's concave up. The rate of change is increasing. The rate of change is becoming less and less negative, which means it's going up. So that interval right there from 1 to 3.5, 1 to 3.5 is where we see the very specific where we are decreasing and concave up. All right, finally, it says determine the end behavior of h as x decreases without bound and express it with limit notation. So I'm going to write my limit. It does say decreasing without bounds. They want me to go towards negative infinity for this function h of x. So make sure you have all those, right? To have the LIM, have the proper notation underneath it for decreasing without bound. That's going to the left. And then don't ever forget your function right here. A lot of kids forget to write the h of x or f of x or g of x. This function was defined as h of x. So what do we see on that left-hand side? Well, we see it going down towards negative infinity. So as the function goes towards negative infinity, or as the as the inputs go towards negative infinity, the function is going down towards negative infinity as well. We clearly see that on the left-hand side there. All right, that's it for the second free response question. In this next problem, we are given a table of values for function g, which is also said to be a polynomial function. Now notice that select values are given, but one is missing. At -3, we do not know the output. It's just listed as b, but we do know that b is a constant real number. All right, so let's take a look at the questions. The first question says to find the average rate of change over the interval -1 to 2. Average rate of change is very easy. Basically, we're finding the slope between these 2 points. So at -1, we have an output of 1, and at 2, we have an output of 13. Again, we're just getting those values from the table. Now to find our average rate of change, I'll just abbreviate AROC. We're going to take 13 minus 1, that's their y minus the y, output minus output, divided by 2 minus -1, that's going to be the input minus the input. So on top we get 12, on the denominator we get 2 plus 1, which is 3, and 12 divided by 3 is 4. So the average rate of change over that interval is 4. And the next question says to find the value of b such that the average rate of change over the interval -3 to 1 is a 1/2. Okay, so basically we know the average rate of change, but we don't know one of the output values right here. So I'm just going to create a little equation. So our first point is -3 comma b. And of course, the b is what we're looking for. And the second point is going to be 1 comma -1. That's looking for that interval from -3 to 1. Now, let's actually go ahead and calculate what that average rate of change would be. Well, it would be b minus -1, subtracting our outputs on top, divided by -3 minus 1 in the denominator. So that's going to be b plus 1 divided by -4. Now we know that the average rate of change is 1/2. So just set that equal to 1/2, and we're going to solve for the b value that would allow this rate of change to be 1/2. So let's go ahead and cross multiply. So we have b plus 1 times 2. That's going to be 2b plus 2 equals -4 times 1 is -4. Then I'm going to subtract 2 from each side, so I get 2b equals -6, divide by 2, and b equals -3. So the value right there for b would need to be -3. That would allow there to be an average rate of change over that interval of 1/2. In the third part, we were asked to explain why function g cannot be an even function. So let's make sure we first explain the definition of an even function. The definition of an even function is when you plug in a negative value, you get the same thing as if you were to plug in a positive value. They're equal. So for example, if I plug in -5 and I plug in +5, I get the exact same value. Well, I want to show why that is absolutely not true here. And there's a couple different examples I could show. For example, we have -1 and +1. We know that +1, the output is -1, and when I plug in -1, the output is +1. Again, those are not the same. These would need to be the same value when I plug in 1 and -1 to get that output or to become an even function. We could also use -2 and +2. So when I plug in +2, I get a 13. And when I plug in the opposite, -2, I get -13. That is certainly not going to meet the definition of an even function. An even function says when you plug in the positive and the negative, you're going to get the exact same value. They're equal. So that's not true whatsoever. So we can use two counterexamples there to show why it is not an even function. Now, the final question says, if it's a odd function, what is the value of b? Now, remember, the definition of an odd function is when you plug in -x, you get the opposite when you plug in +x. Now, the examples we actually already showed using -1 and 1 actually do show this. So when we plug in -1, we get 1, and when we plug in +1, we get -1. So notice they're opposites. So when I plugged in the negative value, I got 1, and that would be the opposite as if I plug in 1, which is I got -1. So these values right here, these outputs are opposite. And the same thing is true for 2 as well. When I plug in +2 and -2, I get opposites. One is 13, one is -13. That is what makes an odd function. So now to figure out what is the value of b, if this is still an odd function, which an odd function is not just true for a couple points, it's true for all points, we're going to look right here. We already know that f of 3 is 117. So f of -3 would need to be opposite of that, -117. So the value of b that would make this an odd function for all of these points shown would be -117. That way each input, whether I plug in a positive or a negative, they result in opposite outputs. So hopefully that makes sense. In this fourth response question, we are shown the graph of a rational function f of x, along with vertical and horizontal asymptotes shown as well with those red dotted lines. We also see a hole in there as well. Now we're asked several questions about this graph and this function, so let's start taking a look. The first says write the equation of the vertical asymptote. That's very easy. We definitely see this vertical asymptote right here at x equals -2. So I'm going to go ahead and write that down. X equals -2. Make sure you don't just write down -2. Write down x equals -2 because it does need to be the equation of a line. All right, then the next question says to write the equation of the horizontal asymptote. We see a horizontal asymptote right here at y equals +2. Same thing. Don't just write down +2. Write down y equals +2, so it's the equation of that actual line. Finally, the question says determine the end behavior of f of x as x decreases without bound. Now, when you have a horizontal asymptote, you are affecting the end behavior. Both the right end behavior and the left end behavior are approaching that horizontal asymptote of 2, so both ends have an end behavior of 2. They're going to get really, really, really close to 2, but never ever get there. So the limit as x approaches negative infinity, because it did ask about decreasing without bound, for the function f of x is going to be 2. Again, that horizontal asymptote affecting the end behavior, both sides, whether asked about decreasing without bound or increasing without bound, both the left and right end behaviors of this function are positive 2. All right, then we are asked to evaluate a couple limits when we are looking at this function. So the first one says, what happens as we approach negative 2 from the right-hand side? Notice that little plus right here means we want to talk about approaching it from the right-hand side. So first thing I do notice, and I do remember, is that we have that vertical asymptote at negative 2. And when we think about approaching it from the right-hand side, we're looking right here. So where is the function going as the x's continue to get closer and closer to negative 2 from the right? Well, it looks like they're going towards positive infinity. When the function approaches that vertical asymptote, it's either going to go straight up or straight down. But on the right-hand side, it's going up. Left-hand side, it would be going down towards negative infinity. All right, what about as x approaches 2 from the left? So at 2, we see that there is a hole. So as we get closer to the hole from the left or from the right, we're actually approaching the y-coordinate of that hole, which looks to be 3. So that's because there's clearly a hole at 2, 3. There's no point at 2, 3, but to identify the missing spot of the graph, we'd write down 2, 3. So that means that the limit as I approach either way, from the left or from the right, as we approach that hole, is going to be the y-coordinate or the missing point of that hole, which is located at 3. We can clearly see that in the graph. All right, the next question says to find all intervals for where the function is less than or equal to 0. Now remember, when you're looking to be less than or equal to 0, you're talking about outputs. Where are outputs less than or equal to 0? And we're looking to be negative, right? That's what less than 0 means, or negative. So if we're looking at this graph, where are we below the x-axis? Where are outputs negative? We see that's going to happen all for these values right here. But we also want to be or equal to, right? We do see that at the 0 of negative 4, we are in fact equal to 0. So to write down the interval where all of those values are, we're going to start at negative 4 with a bracket because we are allowed to equal 0. And we're going to go all the way up to negative 2, but we're not going to include negative 2 because there's a vertical asymptote at negative 2. In fact, negative 2 is not even the domain of this function. Nothing happens at negative 2. But every output between negative 4 and negative 2 is going to have a negative value or equal to 0. That's happening at negative 4. So that's going to satisfy the answer to this question. All right, finally, it says to write a possible equation in factored form for the rational function. All right, this is where we have to understand all of the pieces. So the first thing I want to go through is the hole. I do know that there is a hole at 2, which means that I must have a factor of x minus 2 in both the numerator and the denominator, because those factors would get removed or canceled out, and that's what creates the hole, right? They get removed and create the hole. So that's an important thing there as well. And I also see there's a vertical asymptote at negative 2. That means that I have an x plus 2 factor in the denominator only. So if I plug in negative 2, it creates the denominator to be 0, not the numerator. Remember, holes, when you plug in 2, we need to get a 0 in the numerator and the denominator, which is why I need that factor of x minus 2 in both the top and bottom. Now, I also have a clear 0 at negative 4, so I need an x plus 4 in the numerator. That way, when I plug in negative 4, I get 0 in the numerator only, and I get some particular number in the denominator, but 0 divided by any number in the denominator is going to be 0. Now, the only other thing that we have to account for is that there is that horizontal asymptote at 2. If I stop right now, I have an x squared as my leading term on top and an x squared as my leading term on the bottom. And to find your end behavior, or to find horizontal asymptotes, you divide those leading terms and I get 1. So if I leave it like this, it's going to produce a horizontal asymptote at 1, but I know there's a horizontal asymptote at 2, so I need to put a multiply by 2 out in front of there. That's not going to affect my whole, my vertical asymptote, or my 0, but now my leading term on top is going to be 2x squared, and when I divide those leading terms, the x squared is reduced to a 1, and I just get 2, which is going to produce an end behavior of 2 because of the horizontal asymptote at 2. So those adjustments right there should be enough to write a possible equation in factored form for this rational function. All right, that's it for that question. Let's move on to the final free response question. And this time we're given a analytical form of a rational function. So we have this rational function defined as r of x. We know the denominator is x squared minus 5x minus 14. The numerator, we're just given as f of x, and it's some polynomials. We are told that f of x, the numerator, is a polynomial. Now, the first thing that's going to be really helpful when you're talking about rational functions is making sure you factor that out, right? Always a lot easier to understand what's going on in a rational function if it's factored. So we're going to break apart the x squared with x and x, break apart a 14. First thing that comes to mind is 2 and 7, and I want that 7 to be negative and that 2 to be positive. That way I get that negative 5 in the middle, and they still multiply to get the negative 14 in the back. All right, that's going to come in handy when I start looking at these next couple questions. So the first question says, write one possible expression such that the graph would have a hole at x equals negative 2. Now, let me go back, and again, I already factored that denominator. It's going to be x plus 2 times x minus 7. Now, if I want to have a hole at negative 2, I need negative 2 to turn the numerator and the denominator into 0. So I need to put an x plus 2 in the numerator. That way I get this shared factor that could be removed. That's going to create the removable discontinuity, or the hole at x equals negative 2. So basically that's it. That's going to answer the question. So f of x can be x plus 2. You could add other factors to it, or multiplied by a constant. That's not going to affect the fact that there's a hole at negative 2. Just don't add an x minus 7. But I guess technically you could put an x minus 7 as well. That would produce 2 holes, and it doesn't necessarily say it doesn't have 2 holes, but we know that there has to be a hole at negative 2. So I got to have a numerator with an x plus 2 factor for sure. All right, now let's just write one possible expression for f of x such that there's a horizontal asymptote at 3. Well, again, I go back, think about that factor denominator. We have x plus 2 times x minus 7, which means that our leading term is this x squared. So now if I'm going to have a horizontal asymptote, I need a leading term of x squared in the numerator as well. But I also need a 3 in front of it. That way, when I take the 3x squared from the numerator and the x squared from the denominator, the x squared is reduced and I just get 3. And when you get a constant, when you divide your leading terms, that's going to produce a horizontal asymptote at that constant value, in this case 3. So realistically, that could be my final answer right there, 3x squared. But actually, it wouldn't matter, right? I could put anything after this. I could put a plus 2, x minus 5. It doesn't really matter as long as that leading term is a 3x squared. That way, I divide it by the leading term of the denominator, I get just 3. So simple final answer, really simple, it's just 3x squared. All right, moving on to the next part of this problem. All right, so if the numerator is x plus 4 times x minus 7, identify any vertical asymptotes, holes, and zeros for this function, or state that there are none. So first, I'm going to go ahead and actually put that in, x plus 4 times x minus 7. And then in the denominator, once again, we already know the factored form for that is x plus 2 times x minus 7. All right, so the first thing I notice is that I do have this common factor on the top and bottom, which means 7 is going to result in a 0 on top and the bottom. That's going to produce a hole. So this graph does have a hole at x equals 7. Now, I also see there's going to be a vertical asymptote at x equals negative 2 because negative 2 turns only the denominator into 0. That's going to produce a vertical asymptote at x equals negative 2. And we also see there's going to be a 0 at x equals negative 4 because if you turn the numerator into 0, not also any other parts, that's going to produce a 0 or an x-intercept at that value. So again, I identified the vertical asymptote, the hole, and the zeros for this particular function based on the numerator being x plus 4 times x minus 7. All right, in this next question, we said, okay, well, what if f of x is this cubic function, 2x cubed plus 4x squared minus 7x plus 6? Write the equation of the slant asymptote. All right, so again, anytime the degree of your numerator is bigger than the degree of your denominator, you are going to have a slant asymptote. Well, actually, that's not always true, but it's when you divide the leading terms and you get something that's linear. So for example, if I take the leading term of the numerator, which is now 2x cubed, divided by the leading term of the denominator, x squared, I get a 2x. That right there is linear. That means I'm going to have a slant asymptote. If that was not linear, then you're not going to have a slant asymptote. So how do you find the slant asymptote? Well, we need that long division. So I'm going to go ahead and take my numerator, 2x cubed plus 4x squared minus 7x plus 6. I'm going to divide all of that by the numerator, or the denominator of x squared minus 5x minus 14. All right, so first thing is, how do I turn an x squared into a 2x cubed? Well, I need a 2x. If I multiply x squared times 2x, I get 2x cubed. Negative 5x times 2x is negative 10x squared. And negative 14 times 2x is negative 28x. Now for the one thing that a lot of students mess up is they subtract. You have to subtract these values. So 2x cubed minus 2x cubed is 0. That's exactly what I wanted to happen. 4x squared minus negative 10x squared. Be very careful. Even do some dirty work if you have to. 4 minus negative 10. It's actually going to produce a positive 14x squared. Then I have negative 7x minus negative 28. Again, negative 7 minus negative 28. That's going to turn into negative 7 plus 28, which is going to be a positive 21x plus 6 now. All right, then we're going to say, well, how do I turn x squared into a 14x squared? Well, I need a 14. Pretty simple. So x squared times 14 is the 14x squared. And I got to keep multiplying this out. Negative 5x times 14 is negative 70x. And negative 14 times a positive 14 is going to be a negative 196. Now, I actually could stop right now, but I'm going to keep showing you. I'm going to subtract this. 14 minus 14 is 0. 21 minus negative 70 is going to be 21 plus 70, which is 91x. 6 minus negative 196 is going to turn to 6 plus 196, which is a positive 202. Now, at this point, I'm done, right? Because I cannot take an x squared and turn it into a 91x. So this is going to be my remainder, but you don't need your remainder for the slant asymptote. The slant asymptote is just your quotient. Remainder doesn't impact it at all. So the equation of the slant asymptote for this function would be 2x plus 14 is the quotient when you divide your numerator by your denominator. But it's really important that you understand first, I have to confirm that there is that slant asymptote, and that's when I divide my leading terms and get a linear polynomial like this one, 2x. And the final question here says if f of x is negative 2 times x plus 2 squared times x minus 3 squared, evaluate the following limits. So now before we evaluate the following limits, the first thing I'm going to do is actually write this out, right? So now my numerator is going to be negative 2 times x plus 2 squared times x minus 3 squared, all divided by, again, let me factor that denominator for the 15th time, right? X plus 2 times x minus 7. Now, let's talk about e. E says to find the limit as x approaches infinity. This is asking about end behavior. Now, how do you identify the end behavior of a rational function? You divide your leading terms. So the leading term from the denominator is x squared. The leading term from the numerator is going to be negative 2x to the fourth, because this x right here gets squared, this x right here gets squared. That's going to be an x to the fourth and times that negative 2. All right, I wrote x to the fourth. I said x to the fourth, but wrote, let me just rewrite that. That looks pretty messy. Negative 2x to the fourth over x squared. All right, when I divide those out, I get negative 2x squared, which is a polynomial. And the rules of the end behavior of rational functions says that if you divide your leading terms and get a polynomial, the end behavior of that polynomial is the same as the end behavior of your original rational function. All right, so let's talk about this. This is an even degree polynomial with a negative leading coefficient, which means both ends are going down. Both ends are going down. Again, even, that means both ends are doing the same thing. Negative leading coefficient means both ends are going down. So that means that the limit as I go towards positive infinity or negative infinity is going to be negative infinity. So that's how I figured out that the end behavior as x goes towards infinity is negative infinity. Hopefully that makes sense. All right, the next question says, what is the limit as x approaches negative 2? So what's happening at negative 2? Well, I see that x plus 2 is a common factor on both numerator and denominator. Now, the multiplicity in the numerator is bigger, and when the multiplicities are either equal, excuse me, or bigger in the numerator, that's going to have a hole. So I know there is a hole at negative 2. So now I got to figure out where is the location of that hole. So I'm just going to quickly reduce this. If I reduce this, this x plus 2 is going to cancel with one of the x plus 2's on top. So I have negative 2 times x plus 2 to the first times x minus 3 squared, all divided by x minus 7. All right, so now to find the location of the hole, I'm going to plug negative 2 into that reduced simplified form. So when I plug negative 2 in, I realize I get 0. So in the denominator, I'm going to get a negative 9. But in the numerator, I'm going to get a 0 right here, right? This is definitely going to produce a 0. Negative 2 plus 2 is 0. And 0 divided by that negative 9 is going to be a 0, which means that the location of the hole is negative 2 comma 0. So there's not a point there. That's a hole, right? So that means the limit as I approach negative 2 is going to be 0, the y coordinate of that hole. So once again, let me just quickly remind you, how do you find the location of the hole, the y coordinate? You just simply reduce, getting rid of that factor, and then plug -2 into what was remaining, and it produced a 0. Now, finally, we're asked about what happens as x approaches 7 from the right. Well, what is happening at 7? Well, that's going to be a vertical asymptote because 7 turns only the denominator into 0. And if you turn only the denominator into 0, you're going to create a vertical asymptote. So now I just got to figure out, as I approach a vertical asymptote, am I going up towards infinity or down towards negative infinity from the right-hand side, which is what that little plus sign right there stands for. Now, what I like to do this is I like to kind of think about that vertical asymptote at 7, and if I'm approaching it from the right hand side, think about a number that's just to the right, like maybe 7.5, right? So if I plug in 7.5 right here, it's going to get squared and become a positive. If I plug in 7.5 right here, it's going to be squared and get a positive. If I plug in 7.5 down here, it's going to get a positive. If I plug in 7.5 right here, it's going to be positive because 7.5 minus 7 is positive. So the point is that all those factors are going to be positive if I plug in 7.5, but because there's this constant -2 being multiplied out in front, I'm going to get an overall negative because a positive times a positive times divided by a positive divided by a positive, but multiplied by that negative out in front is going to produce a negative, which means as I approach 7 from the right, I'm going to be going down towards negative infinity. So once again, I just thought about what happens as I have numbers really, really close to 7 from the right. And when I plug that in, I'm going to get a negative, which means as I get really, really close to 7 from the right, I'm going down towards negative infinity. Now, you're not allowed to use a calculator on this problem. That's at least the intention. But you could also, if you had a calculator, go ahead and make a graph of it so you can actually see these things all happening. All right, that's it for this problem. And I really hope that these problems are going to help you crush your first Unit 1 test because there's a really good chance that you're going to see problems just like these when you open up your Unit 1 test. Best of luck.